All right, so today we are graphing tangent, the tangent function. And as you can see, kind of our transformational form here looks very similar to sine and cosine. We have A, which is the vertical stretch. Okay, this time it is not an amplitude. Tangent values don't have an amplitude, as we'll see, because the graphs look very different. B is, so that is our vertical stretch, right? Compression and or if it's negative reflection. B here is actually a horizontal stretch or compression or reflection, but we won't have to do it on the graph like that. C will control whether or not there is a shift horizontally, okay, and you no longer need to refer to that as a phase shift. And then K is our vertical shift. Actually, I think that's not true. I think you can refer to that still as a phase shift. Okay, so this time we only want to graph nice kind of values of tangent. So if we go back to our unit circle, here are some of the nicer values, right? At 0, tangent 0. At pi over 4 or 45 degrees, it's 1. And in fact, let's go ahead and bring in our graph, and let's graph the parent function as we kind of go around here. So here's at 0 degrees, tangent has a value of 0. At pi fourths, or essentially 45 degrees, which would be roughly here on the graph, our value is 1. Okay. However, note that when we get to pi over 2, 90 degrees, remember tangent was undefined there. And the reason it was undefined is we were dividing by 0. And so what does that turn into graphically is a vertical asymptote. Okay, so we end up having a vertical asymptote here at 90 degrees. Then at 135, 3 pi fourths, we're at negative 1. Oops, that did not change colors. So negative 1. At pi radians, tangent is 0. Our tangent value there was 0. At 5 pi fourths, our next 45 degree marker, we're up at positive 1. And then note we are at undefined yet again. So really quickly again, we approach this undefined value at 3 pi halves, 270 degrees. Remember, tangent is always undefined on the y-axis values and 0 on the x-axis. And so, in fact, if you were to go backwards here, kind of fill in some of these negative angles, or if you were to continue the pattern, we end up getting these vertical asymptotes, essentially every 180 degrees, right? Every 4 boxes, I guess, at this current scale. And so that pattern would continue. And then we also get these tangent values that go, there's kind of a 0 halfway between the vertical asymptotes, and it goes up 1 on the right, down 1 on the left, kind of halfway between the 0 and the asymptote. So up 1 on the right, and then down 1 on the left. And then we can kind of visualize where our next points would be. And our graph will look something like this. Okay, so we end up getting a graph that kind of looks like this. And don't worry, guys, it still works with our day at the beach. These are your tan lines. They're tan lines. I mean, they're curves, but you get it. Tan lines, curves. Okay, anyway, so you get these kind of S-shaped curvy lines that are bounded between these asymptotes that they get closer and closer to as we go up and down, right, towards positive and negative infinity. And it repeats every so often here. In this case, every 180 degrees starting from pi over 2, right? Undefined, undefined. Every time we go half a circle around, it's undefined. So that was the parent function. Okay, now notice A is not called the amplitude now, and it is not necessarily a distance. We just refer to it as a vertical stretch, because unlike the kind of sinusoids, right, or cosine waves, there is no amplitude this time. So it's just a vertical stretch. Note that the period, though, remember the period is kind of the space that we need to repeat, right? One full sine, cosine, or tangent function here. And note that we only need to go essentially 180 degrees, pi radians, before it starts repeating. So the period, instead of being 2 pi over the absolute value of b, it's just pi over the absolute value of b. Okay, so this is only 1 pi, so I put it in a different color here, so we note that tangent is a different period than sine or cosine. Okay, the phase or horizontal shift, you can still recognize as the opposite of C over B. Really, we could just say C is kind of the horizontal shift, and B is kind of a horizontal stretch or compression. We won't go too into that this year. And then we just still have K is our vertical shift. So let's look at some steps we're going to need. As you can see, there's a lot of steps here. There's really just 3, but they're a little wordy. Now, we don't graph this like we did with sine and cosine. We're going to graph it a little bit differently because you notice there's so much going on with these graphs in a limited space that if you keep trying to draw these vertical asymptotes over and over again as you do every transformation until you get to the final graph, it ends up looking like a war zone broke out on your graphing sheet. So we do graph these a little bit differently just so it looks a little bit cleaner. And I'll show you a cool way of doing that, which we have to solve 2 equations, but once we do that, we get almost all the information we need. So, all right, so let's walk through the steps here. Identify the vertical shift, K, and mark that as the new x-axis. So nothing really different there. So if we're using our example here, we do have a K value. K is -2. And so we'd go down to -2, and if you want, you can put a dashed line. Just to kind of remember, hey, that's my new x-axis down there. Okay. So that's where my new x-axis will be. Next, it says to solve for x to find our new vertical asymptotes. And so essentially what we're going to do is we're going to take these 2 values of tangent, where tangent is undefined. Okay, whoops, I forgot to write in. This is supposed to be 3 pi halves. Apologies. Those 2 places where tangent is undefined kind of gives me how spaced out these closest 2 vertical asymptotes would be. Now, sometimes though, when I go from pi halves to 3 pi halves, I end up going out of my graphing window. So, and as an alternative to using 3 pi halves, sometimes we can use negative pi halves, which is just kind of going this way, pi halves. Anyway, so that would be kind of an alternate equation. So we're going to solve these 2 equations. When does, remember the inside is kind of the bx plus c, when does the inside equal pi over 2? And when does it equal 3 pi over 2? Okay, so we can do that down below here. Bx plus c is x plus pi halves, right? That's what was inside of our function. When does that equal pi halves? And when does x plus pi halves equal 3 pi halves? So solving these 2 equations for x will tell me where my 2 adjacent vertical asymptotes would be. So you might note here that I need to subtract pi halves from both sides. And wow, we end up getting a pretty nice answer for this one. We get 0. So at x equals 0 is one of our vertical asymptotes. The y-axis ends up being one of our vertical asymptotes. Okay, if we solve the other equation, subtract pi halves from each side. So 3 pi halves take away 1 pi halves would equal 2 pi halves, which is just pi. Okay, so at pi, we have our next nearest vertical asymptote. Okay, so I can kind of use this spacing here on my given scale. 1, 2, 3, 4. Every 4 boxes should give me another vertical asymptote. So 1, 2, 3, 4. And 1, 2, 3, 4. Okay, so what we actually just solved for by doing this, if there was a horizontal stretch, in this case there was not, because b was 1, we would have accounted for that, and we've done the shift. We've actually done 2 of our transformations right there. So that's pretty cool. And watch how easy, now that I've done this, watch how quick it is to graph tangent. Halfway between our vertical asymptotes on our kind of quote-unquote new x-axis is a 0, or x-intercept. Halfway between our 0 and the asymptote is our other 2 points. They'll help us get this S-shaped curve. Okay, so note that my a value here is just 1. So we don't need to do any stretching or reflecting. So that means halfway between my 0 and the right asymptote, we go up 1 on the right and down 1 on the left. Down 1 on the left, up 1 on the right. We didn't have to do any stretching, compression, vertically or anything else. So we're going to get our graph is basically down here. This is really just, and we are going to fill in those individual values in a second here. This is really just our parent function shifted left pi over 2, shifted left 90 degrees. That's kind of a terrible curve, but we'll run with it for now. And then shifted down 2. Okay, so what was our vertical shift? Down 2, right? K was -2. Our vertical stretch was none, right? A equals 1, no reflection either. The period, remember, is different now. It's pi over the absolute value of b, so just 1 pi, and b here is 1. So the absolute value of 1, I just get pi over 1 or pi. The period repeats itself every pi units. I can kind of tell, yep, every pi units it repeated itself. And then lastly, the phase shift is really just opposite of c. So the opposite of c over b, actually. So opposite of c over b would be negative pi halves over 1, which is negative pi halves, and the negative means left. So left pi halves units. So if you compare that with the original graph, we've shifted left pi halves, or 90 degrees, and we've shifted down 2. That's the only difference on our graph. Okay, again, this part of solving these two equations would actually account for the vertical stretch, a period change, or sorry, not the vertical stretch, the period change, and the phase shift. These two parts, so we actually do like both of those at once and draw them in on the graph, which is kind of nice. So let's try another example. Okay, so here's our second one. Let's go ahead and identify all these parts here. Here's A, is -2, so our vertical stretch is 2, and we have a reflection vertically. Okay, so the only difference that we're going to do there, remember from our parent function where we go up 1 on the right, down 1 on the left, when we do a reflection, it's just down 1 on the right, up 1 on the left, and your graph would come in this way instead, if that makes sense. So it's pretty easy to perform a reflection on here. Okay, our vertical shift, there is none this time. Our k value is 0. Our period is pi over the absolute value of b, so just 1 pi. Our b value here is 2 this time, and so we get pi halves. It will repeat itself every pi halves units. Okay, and then our phase shift, opposite of c over b, would be opposite of c, would be positive pi. This is c, and this, of course, is b here, over b, which is 2. So our phase shift is pi over 2. Because it's positive, that is right pi halves, or 90 degrees. Okay, now to actually graph this in, the first thing we're going to do is we graph where our k value is if there was a vertical shift, and since there is none, the x-axis plays itself. It plays the x-axis. Okay, next up, let's solve our two equations. When does the inside here, 2x plus pi, or sorry, 2x minus pi, when does that equal pi over 2? Remember, that was one of the original undefined values for tangent from our unit circle. And when does 2x minus pi equal 3 pi over 2? That was our second undefined value. And so this will kind of tell us how spaced our vertical asymptotes are and where they're at. So let's solve for x. Now I need to first add pi over, and because I'm going to want a common denominator, I'm going to write that as 2 pi halves when we go to the other side. So now I get 2x equals 1 pi halves plus 2 pi halves is 3 pi halves. And when I divide by 2, that's the same as multiplying by 1/2. We end up with x equals 3 pi fourths. Okay, we'll come back and graph that in a second. Let's do some similar operations over here. Adding a pi over, again, I'm going to need a common denominator. So let's do 2 pi halves, the equivalent of 1 pi. So now I get 2x equals 5 pi halves. And when we divide by 2 or multiply by 1/2, we get 5 pi fourths. Okay, so 3 pi fourths, 5 pi fourths. Ooh. Well, let's see. If this marking is a pi half, halfway should be a pi fourth, right? Half of that. So if this is 1 pi fourth, 2 pi fourths, 3 pi fourths, right? Every box essentially is a pi fourth on this scale. So here's 3 pi fourths. That is 3 pi fourths. I'll kind of mark it. And then this would be 4 pi fourths, 5 pi fourths. And you're going to go, uh-oh, we're going to get a lot of these tangents repeating if I were to graph in the whole thing. Maybe we won't graph in the whole thing. Maybe we'll just do a few of them here. And we'll just understand that it looks like every 2 boxes then, at this scale, we're going to get another tangent graph. Okay, so maybe we'll just do these ones and we'll move on from here. So now again, halfway between our asymptotes is always a kind of a 0 or a point on our new x-axis, which is the original x-axis because k was 0. Now we're going to use our vertical stretch. Okay, so instead of going, remember, halfway between our 0, and our vertical asymptote, we would normally go up 1 on the right and down 1 on the left. However, this has been stretched, so we'd go up twice that distance, right? Since our a value is 2. So this is what it would look like if there was not a reflection, but we do also have a reflection. So we're going to go down 2 on the right and up 2 on the left. And again, this is just halfway between my 0 and my asymptote. And we get this very kind of stretched out looking tangent value that's been reflected. And our period change has been altered quite a bit. So again, halfway between them, up 2 on the left, down 2 on the right this time because of the reflection. And we'll get some graphs that look something like this. And they would just repeat themselves over and over and over again. And we get the, hopefully, kind of the idea. This would be up here and here. And that would start to go off the graph, and we could fill in the rest. But there's example 2. Okay, let's do one more. I know these take a little bit. They're new. I'm talking a lot. Hopefully that's helping and not just annoying. All right, so example 3. Notice this one's got a ton of stuff going on. That's fine. Let's walk through it. 1, our k value. Is there a vertical shift? Yes. Up 1 unit. Let's mark that on my graph. Positive 1 is my new x-axis. That's where my zeros will be. Okay, next, is there a vertical stretch? In this case, it's a compression. Of 1/4 and a reflection vertically. Okay, so instead of going like up 1 unit on the right, we'll go up 1/4 of a unit on the right. And in fact, because we're reflecting, we'll actually be going down 1/4 unit on the right and up 1/4 of a unit on the left. That won't be too hard to do. So let's go ahead and actually calculate these individual values. The period, the absolute value of 1 pi over b, b, pi over the absolute value of b, I can't speak. So here our b value is -1/2. So again, remember absolute value is going to change that to be positive. When you're dividing by a fraction, that's the same as multiplying by its reciprocal. The period ends up being 2 pi. So we're going to get more, this ends up being a horizontal stretch and not a compression. B is kind of the reciprocal of what A does to the graph, if that makes sense. Like this is actually a compression vertically, but this is actually a stretch horizontally. So instead of only requiring 1 pi for a tangent to repeat itself, it's now going to require 2 pi. It's going to be stretched horizontally. Okay, our phase shift, opposite of c over b. Here's my c value, negative pi fourths. So the opposite of that is positive pi fourths divided by b, which is negative 1/2. Here you don't do absolute value. Let's multiply by the reciprocal. Since we were dividing by a fraction, we get negative 2 pi fourths, which reduces to negative pi halves. Because it's negative, that is a shift left, pi halves units. All right, well, to find where our asymptotes are, let's set the inside here, bx plus c, equal to pi over 2 and 3 pi over 2. So when does negative 1/2 x minus pi fourths, it's going to be a lot to solve here, equal pi halves? And when does negative 1/2 x minus pi fourths equal 3 pi halves? All right, so let's start by adding pi fourths to both sides. But we're going to need a common denominator here, aren't we? So let's multiply this by 2. That's going to become 2 pi fourths plus 1 pi fourth will become 3 pi fourths over here. So I was making this one 2 pi fourths so that they had a common denominator. Now let's divide away our negative 1/2, which is the same as multiplying by its reciprocal. So multiply both sides by negative 2, essentially, which I don't know why I didn't write over there, but it's fine. We get negative 6 pi fourths, or negative 3 pi halves, if we reduce. Negative 3 pi halves, okay, is where one of my asymptotes will be. We'll figure out where that is. Let's do the math over here as well. Add a pi fourth. Now we're going to need common denominators again, so let's double this top and bottom. So 6 pi fourths plus 1 pi fourths would be 7 pi fourths. Negative 1/2 x. So I should have written it this way last time. Dividing by a fraction is the same as multiplying by its reciprocal. So you can show those cancel. And we get negative 14 pi fourths, which is negative 7 pi, well, that's a pi, pretend, fourths. Negative 7 pi fourths. Whew, okay, well, let's figure out where these are. So we said earlier that if this is a pi halves, this would be a pi fourth. Now we need to go, let's see, negative 3 pi halves. So 1, that's negative 1 pi half, 2 pi halves, negative 3 pi halves. Actually has its own marking there. So here is where one of my asymptotes are. Okay, negative 3 pi halves. Sorry, that's on the orange there. It's probably hard to see. And then negative 7 pi fourths. So 1, 2, 3, 4, 5, 6, 7. Oh my. Wait a second. Did we mess up a sign somewhere? Okay, yeah, whoops, this is halves, right? Negative 7 pi halves. Which, that's way off my graph to the left. So this is where we put in this alternate. Rather than 3 pi halves, let's try negative pi halves. So we're going to solve this one more time. I know this is kind of a lot, but let's try negative pi halves instead and see if that keeps me in my graphing window. So that's kind of, this is the alternate. Like tag this one in if 3 pi halves takes you out of your graphing window. So we're going to add over pi fourths again, plus pi fourths, multiply this by 2, so that's negative 2 pi fourths, plus 1 pi fourth, it's negative 1 pi fourth. Multiply both sides by negative 2 over 1, or negative 2. And we end up getting positive 2 pi fourths, or pi halves. Positive pi halves. That is in my graphing window. Here it is, positive pi halves. And look at this, man. Those are the closest two asymptotes we could fit in our graphing window. So you can see it's way more spread out. Okay, but we're ready to graph in everything. Now that we've done all this work, halfway between them, which looks right here as pi over 2. There's our 0. Now, remember, we do need to use a here. So normally, halfway between those, we'd go up 1 on the right and down 1 on the left. Whoops, down 1. But we are only going a quarter this time. So a quarter of a unit up on the right, a quarter on the left. But then there is also a reflection. So actually, we're going to go down on the right and up on the left, just a quarter of a unit. So my graph is going to be very kind of wide in here as it curves between these asymptotes. And then I can kind of use this scale. What is this? 1, 2, 3, 4. 2, 3, 4 would be a 0. And then halfway here, we'd be going up a quarter of a unit, down a quarter of a unit, and it'd be doing something like this. Or here we'd be going down a quarter of a unit and kind of coming in something like that eventually as we leave our graphing window. So not a whole lot we could fit in there. Okay, so tangent, couple things that are different. One, the period is only 1 pi over the absolute value of b, not 2 pi like sine and cosine. And in order to not just have a million vertical asymptotes drawn in and shifted, if we solve these two equations up here, we can figure out where 2 of the closest asymptotes are, and then kind of use this pattern of where our other 3 points are, our 0 and our other 2, to kind of quickly finish the tangent graph. I know it does require you to solve some equations. That's not always the most fun, but once you do that, you've essentially done a lot to identify key parts on your graph. Okay, that's it. We will do several examples in class. Make sure you ask any questions that you still have.